these have the same scaling factor. It's taking the same square root of a scaling factor, but this is the same factor. So that means the proportional relationship between these things are going to be the same. Professor Wolfram was talking about energy and momentum in this, and that's kind of what we may have stumbled upon. Okay. Methodology in Wolfram physics. We chronicle the process of how we came to our speculative yet seemingly, quote-unquote, in good agreement with physics project estimates of elementary units. Our investigation, like many others, took a number of twists and turns, so to speak, and on the day of mid-project meetings, 2 key pieces of information were obtained. During lunch, Xerxes stressed the idea of energy and momentum having a strong meaning within our graph structure, and the assignment by Professor Wolfram of additional reading. Yes, I got homework. This built upon guidance from program mentors of focusing on length, time, and energy. Okay. No, you give shout-outs to the people that were helping you. Duh. So as we can see, this is from... I'll bring up the Wolfram units. Physics. Okay. This is terrible. I need to read so much more. God. I might just be the luckiest son of a gun in the world. I have no idea. Okay. So as we can see here, this is from the page and I highlighted it. Anything we directly observe must ultimately have a signature in the causal graph, because that's the stuff that's happening, at least within my knowledge of the Wolfram physics framework. And a potential hypothesis about energy and momentum is that they may simply correspond to excess fluxes of causal edges in time and space. The wonderful part about any program where you're actually in person is I was in line, all of a sudden, wild Stephen Wolfram just appears behind me while we're waiting in line for lunch. And I'm like, actually, no, that's incorrect. I asked him, after he did an interview with one of the other attendees at the summer school, apparently, maybe I was just supposed to ask him to do an interview there. I don't know. People come from all over the world, and I live close enough. I didn't want to hog all his time, so to speak. All right. I talked to him after. I'm like, yeah, I had done some homework, and I found an interesting connection and I was mentioning how you suggested this was a potential hypothesis about energy and momentum. He's like, no, it's no longer a hypothesis. He's like, I'm pretty sure, that's how it has to be within this framework. And I'm like, well, your initial estimates seem to be quite spot on, even though we got the... Let's get to it. I'm sorry, I'm bloviating. Oh, God, my terrible little thingies. Okay, upon doing assigned homework, so to speak, this passage was come across. Coincidentally, we had considered using the Planck intensity as a method of estimating potential activity within our graph network. Big G over there. Okay. Standard quantum mechanics, in effect, defines h bar, the elementary unit of action through energy, equals h bar, Planck's reduced constant, times frequency. Because if you do this out, you get a mass. You get... so h bar is its mass. It's basically the Planck mass times Planck length squared divided by the Planck time. If you add in another frequency in the denominator, you're going to get energy. So that's just kind of how that works. But in this relationship, E is a measured energy, not the energy associated with a single causal edge. And to convert between these, we still need to know, in effect, the number of states in the Bronschild graph associated with our quantum frame, or the number of nodes in our current slice through the multi-way system. We'll call this number Z. Or that number there. Okay, I'm sorry. It's the syntax. The syntax gets me. It's the same thing, just slightly different font. Oh God, this is bothering me. An alternative interpretation for determining Z. Our original, hold on. It's Xi, because it's the same as Xi Jinping, the China's premier, I think, or prime minister. Our original technique failed, yielding results off by 17 orders of magnitude for physics project estimates. So basically I was like, okay, well, if this is the intensity within this, it was way off. It was way off. However, Having taken Xerxes' advice at lunch, advice during lunch, we simply divided the energy out, i.e., we took the Planck intensity and divided out the Planck energy, resulting in the Planck flux, or basically within Planck units, it's 1 over Planck length squared, or Planck area, and then times the Planck time. So you can see that with little table here, the property of the expression is, that's capital I, so it's Planck intensity divided by the Planck energy. It gives you this value here, that 7 times 10 to the 112 ginormous things interpretation. Flux energy rate per area per energy unit. Okay, so this is a dimensional number though. Therefore, we must do the naive thing and multiply our reference ones for SI units of flux, which yields. So basically, you need to multiply it by meters squared and then seconds to just get a dimensionless number. To be fair, that's what I wanted to figure out if it made any sense doing that, because I'm still speculative about that. I can say words, I can make arguments, but I don't know. So it gives us this value and everything. And yeah, there's a little bit of code there. I think we can. I have it written a different way. Okay, well, let's do it. No. Okay, so as we can see here, we just do that, gives us a dimensionless number. So the generic interpretation actually come up, this was GPT 4.0 or maybe the notebook, I'm going to say probably GPT 4.0. Planck space-time cell count in a given volume. I'm like, oh, is that like a pixel, a voxel or something? It says it's scalar. Okay. There is a philosophical argument that could be made that if our hypergraph structure is literally the literal underlying medium for flux, quote unquote, that we may take this dimensional count as it appears. Because if it's the flux through the graph, and this ends up being the dimension of flux, according to Wolfram alpha, and again, so many of these things I would not have known unless I went down multiple Wolfram holes for years, and that was one reason I knew the Planck intensity was a thing. Just combining all these expressions, what happens when you do this, what happens when you do this, because I'm a gamer, and also probably kind of spectrum-y, so I'm like, yeah, I'm going to try all these combinations and see what happens. All right. So the medium of flux, that we may take this dimensional count as it appears. So I'm making the argument that maybe we can just take this as the literal count of flux edges. This is quite reckless, and we should caution the reader, again, this is a speculative result, because it's such a crazy result, and it's like, listen, before people latch on and say this is how it is, it's like, caution. Proceed with caution. However, taking this numerical count of flux seriously and plugging it into our framework for Z leads an elementary length of the magnitude. So basically, we're taking this ginormous number here, we're taking the square root of it, so we're raising it to the 1/2 power. That result leads to a Planck intensity times, this ends up being the scaling factor. Because let me go to the Wolfram pages real quick. So this is easier to explain if we actually go over here. So let me stop sharing for just a moment, and then we'll just go through real quick the Wolfram methodology, so to speak. All right. So units and scales. Okay. So this is where I spend probably the most of my time on it, because they're going through. It's like, all right. Once you have an elementary time, well, you basically just divide it by C, or basically if you have an elementary length, your elementary time is going to have a magnitude. If you're using Planck units here, we'll have that about 8 magnitude, or basically the proportionality factor of C between those, given our coherent unit structure. Okay. So basically the whole thing is they go through and they're estimating. You keep on seeing this thing, so it's like, so elementary time is Planck time divided by the square root of this scaling factor, G. So as you can see here, they're just taking the generic magnitudes. They don't even have any of the significant digits or anything there. They're just taking those rough magnitudes, and then the energy is going to be Planck energy, blah, 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 10 to the 9 joules. Okay, so LP, TP, and EP are the Planck length, time, and energy. Okay. Now, the thing is, they're trying to estimate G. So the crazy thing is, they went by in a completely different method. It was computed by estimating time of universe. So I think they use the Hubble time in here. So yeah, you got the Hubble time divided by the elementary time, and then you got this K proportionality factor, which probably should be investigated more because speculation. Okay, so they have all this stuff. So long story short is, I think this is the almost quadratic recurrence constant, because so they have this transcendental equation. So they're plotting it to try to estimate that as a function of k. So they're getting that about 10 to the 61 number. We had like a 10 to the 57 number or something. Okay, so they have this. So long story short, that scaling factor is somewhere between 10 to the 112, and they're estimating maybe 5 times 10 to the 117. They're estimating it 10 to the 116 because it seems to be within the magnitude of this calculation. You can believe whatever you want there. So long story short is, they get these elementary units by using that scaling factor. So they're literally, and again, they're not even using any of the significant digits, just the exponential powers to determine an elementary length of about 10 to the 93 meters, elementary time about 10 to the minus 101 seconds. So that's how they're going through and doing that. And then the other part is, so this is the maximum entanglement speed for an observer. Okay. So they're literally just doing, it should technically be frequency, which would just be 1 over the elementary time. But they're saying, in connecting to observable features of the universe, it seems better to quote in terms of the energy associated with the edges in the causal graph, in which the results based on our estimates is elementary energy divided by elementary time equals this. It's about 10 to the 52 watts, so that's about like 5 solar masses a second. This seems very large, blah, blah, blah. Now, if you just go to Wolfram Alpha and you realize, one, these units are based upon Planck units, okay? And if all these units that we're going through here, like elementary energy and elementary time, these have the same scaling factor. It's taking the same square root of a scaling factor, but this is the same factor. So that means the proportional relationship between these things are going to be the same. So this is just going to end up being whatever a smaller version of the Planck energy. This is going to be a smaller unit of the Planck time, but they're going to be scaled. Let me just show you. Because all it is literally the Planck energy divided by the Planck time here. When you see this whole thing at the bottom. That zeta, a maximally entangled observer, so to speak, whatever that might be. Now, it could be compared to maybe an astrophysical process, maybe, but, so if you just take Planck energy divided by the Planck time, and you don't drop the numerical factors there, it tells you it's the Planck power, because that's what it's going to come out to be. Now, you can do more and stuff. I feel like a lot of this just comes from a lot of folks they're programmers. They work within the mathematical style notebooks. And you can do these general calculations. If you want the full relationship, you can query Wolfram Alpha, and it will eventually give you some things and stuff. But this is also one of the reasons, this is also how Dad taught me. So all the stuff is just given directly right here. So that's the only reason why I knew. And yeah, so you got an energy. You throw one more time derivative down below there, and it gives you the dimension of power. And it tells me it's the Planck power. So I'm like, well, according to this, if we take this seriously, that would mean a maximally entangled observer is outputting the Planck power. What does that mean? I could highly speculate on that, but that's not for our current discussions.